Now, why is this equality? Why is this function actually, or this function gives us this term here? Well, it's very easy. So if we just consider F times L times F transposed, well, L is nothing else than D minus F. So we can rewrite this as this one here. Yeah, and D, well, F times D times F transposed. Well, D is a diagonal matrix, yeah? So we can rewrite that as just summing up all the diagonal elements of D times F transpose, which gives us actually Fi squared, yeah? And this one here is an n times n matrix, sorry, the W. So we have to sum up all the pairwise elements times the corresponding F values. Yeah, so that can be rewritten as this one here. Now here comes a trick, a little bit, a mathematical trick. Well, we well, in German we would say wir klammern aus, ein halb aus. Yeah, so we put, well, we have A minus B, and that is of course the same as 2a minus 2b times divided by 2. Yeah, so we just get out 1 divided by 2, 0.5 out of this term here. Yeah, so this is a here. Yeah, so we get a. This is a again, which is this one here. And this is the second term here, yeah, a, and this is 2 times b, yeah, minus b. So we have a minus b, and now we have 1/2 of times 2a minus 2b. Here is 1a, here is the other a, so we have 2a, and here minus b. Okay. Okay, and why is that a and that b here? Well, of course. D, if you remember, D is just the weighted sum, or the sum of the weights. Yeah. So where is D? Here is D. D is the sum of the weights from the corresponding entry, from the corresponding node. Yeah. So we can replace DI here by the sum of the weights from I to all the other J's that are connected to I. Yeah. And the same down here. Yeah, and this one here just remains as the same, but we just take 2 times this one here, 2 times this one here, yeah, 1, 2, and then take half of this this term here. Yeah, yeah, and then we go on with just recombining the whole things. Yeah, so this is obviously we can combine these two sums into one sum, like this one here. Yeah, and this remains as before. And then we can have a kind of binomial formula and take this as one big sum here and take the corresponding f values together, which then runs down to a binomial formula here, a squared minus 2ab plus b squared, which gives us a minus b squared. Yeah. And yeah, that's exactly the right-hand side of this formula here. Yeah? So this function here is actually exactly probably what we want, yeah? Because if we know that if we minimize this one here, then we have probably a very good partitioning actually. So let's have a look at an example with these indicator vectors in this Laplacian matrix, and actually how that works. So here's a special case. The graph actually consists of k connected components here, k equals 3. Yeah, so these k connected components are obviously the best way to partition the graph, because there are no edges between these k components. So is a kind of natural way to take these k components as the k clusters. Yeah. So the k components yield a perfect cluster, no edges between the clusters. That means we have an optimal clustering by the indicator vectors. So the first 3 nodes or objects are the first connected component, all the others are not. The second 3 the second three objects are in the second cluster, the second connected component. The first ones and the last ones are not, and then the last three are in the third connected component. So FC3, that should read FC3, of course here. Sorry for that. Yeah, so they are in the third connected component in that case. Yeah. So that is a perfect cut, because we don't have any connections between the first three nodes and the others, and no connections between the second three nodes and the others, and so on and so on. Yeah. So here you see the adjacency matrix. Yeah, you see here these three here have only connections. So here are only connections within each other, but no connections to the other nodes here, and the same holds true for the other one. Yeah. So here's the weighted adjacency matrix. Here, that would be the degree matrix. Yeah, just sum up all the in and out degrees, weights of these nodes here, and that would be the Laplacian, which is d minus w. Yeah, and because of the block form here, because it's an optimal clustering, actually we get in that case FC times L times FC transposed equals 0 for each of the components. Yeah, and you see here that is because we have this block form of the Laplacian, which indicates that these blocks here are perfect connected components. They have no links between these connected components, so that is a perfect clustering, meaning that the optimization function here is really at the optimum that we can get. Yeah, because we said that this one here is semi-definite, positive semi-definite, meaning that it cannot be better than 0. Yeah, so 0 is the best possible cut we can have. Yeah, but very often we cannot have a better cut or a cut that is equal to 0. We can only have a cut which is equal to 0 if we have really k connected components. Yeah, like we do here. Yeah, so the general goal is to find indicator vectors that minimizes, of course, this optimization function, and there is a trivial solution for that, where we just put once in all the components. So in that case, that would be a trivial solution, which is obviously not what we want. Yeah. The problem is finding a solution is still NP hard, because it's still a graph cut problem. And the question is, how can we relax the problem to find a good solution which is more efficiently? Yeah? So an approximate solution to this problem here. And so you may say, hey, come on, we did all that shitty mathy stuff here, do the pump up the complexity of the problem in order to achieve nothing. Yeah, but it's because it's still NP hard. But actually there is a kind of twist about all that stuff, which gives us an idea how to actually come up with a good approximation or a good heuristics. So it was worth it, so to say. So it was not for nothing, and that is because the following observation holds true. So for the special case with k connected components, the k indicator vectors fulfilling this optimization function equals 0 yield the perfect clustering. Yeah? And the indicator vector for each component is actually an eigenvector of the Laplacian with an eigenvalue of 0. Yeah? Oh, that sounds good. And the k indicator vectors are orthogonal to each other, so they are linearly independent. So wait a minute, if the indicator vector of each component is an eigenvector of the Laplacian, maybe we just try to get the first k eigenvalues of 0 in the best case, but if the eigenvalues are not 0, meaning that there is no perfect cut in because we don't have k connected components so far in the graph, we could just take the eigenvectors of the Laplacian with the smallest eigenvalues. So they should give us the best k components out of this graph. right? And that is exactly the idea. So first of all, the lemma here, the number of linearly independent eigenvectors with eigenvalue 0 of L equals the number of connected components in the graph. Yeah, so it gives us an indication how many connected components are there in the graph. Well, okay, nice. So if we want to have, and very often we don't have any connected components. Yeah, we just have one big connected component, which is the whole graph. Yeah. So if we want to cut this connected graph into k components, we just look for the k eigenvectors with the smallest eigenvalues. Those are the indicator functions, the indicator vectors. The eigenvalue vectors are the indicator vectors for those k clusters, k connected components. Yeah?